Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery that's coming from an exoplanetary telescope that has just found what seems to be a collision of a star with a black hole, and more specifically, the so-called tidal disruption. So this beautiful telescope known as TESS is technically the new high achiever. It's the one that's going to be able to discover several thousand exoplanets in the next few years, and it's already discovered quite a lot of really cool things. But this particular study, the paper for which you can find in the description below, was basically a complete accident, because first of all, it wasn't really originally detected by TESS, it was discovered by a completely different telescope, but by using TESS and also combining it with various other telescopes from around the world, the scientists behind this paper were able to figure out that what they're looking at is essentially a supermassive black hole destroying a star and creating these very unusual effects. And all of this began with the detection by ASSASSIN, which stands for All-Sky Automated Survey for Supernova. It's basically a system used by the scientists to, as the name suggests, detect supernova around the night skies. And it was then followed up by several other observations just to make sure that what they're looking at is exactly what they thought they're looking at. A black hole having a bit of a snack. But this is how the scientists knew that this particular event was not a supernova but instead something else. Here you'll notice that the way that the brightness increases is very gradual. It's not an instant flash as you would expect from a supernova. And we've seen this around other black holes during the so-called tidal disruption events. Now, the way that it works is actually pretty easy to simulate using Universe Sandbox. Here we have a very massive and extremely large supermassive black hole in the middle of a galaxy roughly around 350 million light years away from us. And it's a little bit more massive than the one in the middle of our own galaxy. Here the mass is around 6 million masses of the Sun. And just like our own black hole, it has a lot of stars orbiting around it, and some of those stars might occasionally come accidentally too close to the actual black hole, or might even get swallowed by it. Now, we haven't really seen this happening around our own black hole because today we believe these events are extremely rare. We think that it takes maybe around 100,000 years per galaxy for this to actually happen. And here we believe that a star very similar to our own Sun most likely unfortunately made it too close to the black hole. So let's try to simulate this using Universe Sandbox and see what happens to the star. And you'll notice that as soon as it approaches the black hole, due to the actual tidal effects from this very massive and very dense object, it starts losing pretty much the entire structure here and turns into this really long spaghetti-like shape of star matter. Eventually, all of this will actually enter the accretion disk around the black hole, but right now what you're seeing is the effects from the supermassive object right there in the middle. So this is kind of what we think happened. We don't really know how close the star approached or if any of the matter actually did make it out of the black hole like it did in this simulation, but eventually all of this will probably enter the black hole through the accretion disk, and some of it will fall into the black hole, but some of it might actually turn into the astrophysical jets. So all of this will probably look something like this. This is just an artist's representation of this event. Now here's another simulation made by NASA that shows you exactly what they believe happened, kind of very similar to what we've recreated in Universe Sandbox, but a little bit more realistic in terms of the actual properties that we've observed. But what's really exciting about this particular discovery is that it was actually discovered by an exoplanetary telescope, the one that has a very unique way of looking at various objects in an extremely large area of the night skies. So if it wasn't for the TESS telescope, we wouldn't really have so much detail here. And one of the biggest discoveries from this paper is that it turns out that for some reason the temperatures around this object drop quite dramatically when the actual black hole starts shredding apart the star. We don't really know how to explain this yet. There are some ideas, but this is still kind of unknown. But as you can see here, within about 10 to maybe 15 days, the temperature drops by a very large amount. And this is when the actual peak of brightness also starts increasing almost to the max. So at the maximum peak of brightness, we get some of the lowest temperatures from this black hole, specifically from the accretion disk of this black hole. Now it's not entirely clear what's causing this and why it's happening, but this is something that we'll need to try to explain in some of the future studies. At the same time, the emissions from this event produced a tremendous amount of ultraviolet light, but not really that many X-rays, and this is something that scientists can't really explain either. For a lot of these events, the tidal disruption events, when a star basically gets shredded by a black hole, we do seem to observe similar pattern. Very high UV light, very low X-ray light. Now UV light is obviously a lot less energetic than X-ray light, which is why it's kind of interesting because we don't really know how exactly this is happening. Although one explanation suggests that maybe the main reason for this is because a lot of this light gets absorbed by the dust around the accretion disk, and so we're just not seeing all of it coming out. Although it's kind of hard to tell at this point. And I guess the major mystery here is, of course, this unusual drop in temperature. Right now, it will probably take a lot of thinking and trying to decipher the data to try to understand all of this, but this is something that I'm sure scientists will figure out at some point. The other thing about the study that makes it really exciting is that, well, first of all, it actually took a really long time to get this data and to process it. The way it currently works with TESS telescope is that it doesn't actually send us the data right away. TESS actually received all of this data back in January of 2019, and it basically took about 2 months to finally get this data and to process it and to actually make it available to everyone. So there's still a bit of, I guess, inefficiency in the way that this data is processed from TESS, but it's also because of the complexity of the mission and the complexity of the telescope's orbit. The way it orbits, it can only send data every 2 weeks to us. But nevertheless, we can still receive this data and process it later on. At the same time, by combining the data from TESS with the data from other telescopes, the scientists behind the study were able to get a very thorough analysis of what's happening in the system 350 or actually 375 million light years away from us. And after all of this data processing and after all of this analysis, very recently they were finally able to release their results. So it did take a long time to get all of this, to process all of this, and to write a paper about it, but we're getting much better at doing this. Unfortunately though, we're probably not going to be seeing a lot of these events, especially in the closer galaxies, because the modern statistical calculation suggests that this really happens very rarely. And just to give you a comparison, in our own galaxy we believe this happens roughly around every 100,000 years, whereas a supernova will happen every 100 years. So this is how rare these unusual events are. So being able to detect this event in action basically right after it started is a huge achievement. We've never really been able to see these events in so much detail and get such an extremely well-processed data from all of the telescopes combined. Eventually this will of course help us understand black holes, help us understand how stars interact with black holes nearby, and at the same time will help us either prove or disprove certain theories we have about everything from star formation, black holes, and of course our understanding of the universe in general. Now maybe in the next few years we'll be able to detect another one of these events a little bit closer to home so we get even more data, but for now this is probably the most accurately described black hole tidal disruption event that we've seen basically since the beginning of astronomy. Hello wonderful person, this is Anton, and in this video we're going to be talking about new research regarding black holes, and more specifically the research that in some sense proves Stephen Hawking unfortunately wrong, while at the same time returning us back to the mystery of the so-called information paradox. So before I start, I need to briefly explain to you what information paradox refers to. It's got something to do with black holes. It's the idea that was very thoroughly explored by Stephen Hawking, and in some sense he was one of the few scientists that was very close to finally explaining it. But there was a problem, we didn't really have any experimental proof. Now what exactly is this idea? So first of all, when it comes to black holes, I think most of us already know that they kind of absorb all of the stuff, all of the matter, all of the light, and nothing can ever escape them. But where does this stuff go? And most importantly, what happens to the information of this stuff? What exactly do I mean by information? Well, for example, if we find a black hole that's slowly consuming the matter and various molecules and atoms of hydrogen and helium from this beautiful star right here, what happens to the atomic information of that hydrogen and helium? For example, things like the location of electrons when they got consumed by the black hole, and various other structural information. Because in physics, the idea is that you should be able to technically reconstruct anything as long as you have the information about this particular object. So in other words, if I were to run time backwards, and instead of the black hole absorbing all of this stuff, now all of this stuff is coming out of the black hole, this information has to be reconstructed. But it just so happens that because of the way we believe black holes are, all of this information seems to be sort of destroyed. We don't really know if it's actually stored anywhere, and this is where the information paradox begins. The current understanding is that it seems like the information just disappears, and if we were to run the time backwards, this information would not be reconstructed in any way. So this is where Stephen Hawking tried to explain this by making a few assumptions, and one of those assumptions was that maybe black holes have something he referred to as hair. These very unusual, very difficult to explain and very difficult to describe structures that were made out of possibly some subatomic particles, something he referred to as soft photons, and a lot of other things that are sort of stored on the surface of the black hole, very close to the actual event horizon, and disappear slowly with the so-called Hawking radiation. In other words, he believed that maybe all of the black holes in the universe are in some sense unique. They store this information in this very unusual concept of hair. So he basically proposed a lot of ideas and a lot of scientific concepts to explain how this information can be stored. But in order for us to see if he's right or not, there is actually a way to test this by looking at the black hole collisions. Now, in the last few years, we were able to detect quite a lot of them, but this one right here, this is the original collision from 2015, really redefined our scientific understanding. So when two black holes collide, if these two black holes actually do have, I guess you can call it hair, if they're hairy black holes, if they have some sort of a way to store the information that fell into them, there would be a way for us to hear it. As they collide, they create the gravitational waves, and these waves can then be converted into sound waves. If we look at them and if we actually try to hear them, it sort of sounds like this. Now, this is a video that was made by LIGO Institute, and here is my rough recreation of this sound. Essentially what you're hearing is two black holes slowly approaching each other, and as they do, the actual frequency increases because they get closer and closer, and at some point you hear this chirp. But right here, right at the collision, as soon as the black holes collide, there's also a kind of an overtone. And this is something that we've been looking for, because this overtone can really show us what's happening here. Now, in order to understand why this is important, the best explanation I can give you is think of a typical bell. I'm sure all of you know what a bell sounds like, but you know that every bell is a little bit different. As a matter of fact, even if you take exactly the same looking bells, their atomic structure is going to be different. So when you ring them, their waves that they produce and the overtones they produce are going to be very complex and quite different from each other. And since the collision of two black holes produces a very similar frequency pattern as a bell ringing, we can actually analyze the overtones that are produced by these collisions and thus see if these two black holes are in some way unique, just like the bells here on Earth, or if they're all exactly the same. In other words, if they have hair and are all very unique in every single way, or if they're all identical, hairless things, objects, whatever you want to call them, that possess no identity and thus present no information on the surface. The first such paper that just came out studying this idea of no hair theorem and trying to prove it essentially analyzed the very slight overtones of this first collision. The scientists in this paper found a way to hear these overtones and were able to then discover that unfortunately the black hole overtone produced was basically hairless. In other words, there were no signs of any kind of unique identity in these black holes, or in other words, that all of them were hairless. And these black holes were identical in pretty much every major way except for the three main properties. Their properties being mass, momentum, and charge. Everything else about these black holes was pretty much identical, suggesting that the information is just not there. It's either lost completely, and thus the so-called information paradox is still a paradox, or it's stored in some other way we can't really imagine yet. Now, just for fun, I tried to create this ringing effect just to hear what it might sound like when these two black holes collide, and based on the information in the paper, right after the black holes collide, it probably sounds something like this. At least that's my best interpretation of the event. It's still very uncertain what really happens with black holes and what really happens inside of them, but also what happens to all of the material and all of the matter and of course information that is unfortunate enough to enter the black hole's event horizon. But by establishing this very specific technique that was used to study the overtones of these black holes, these scientists will be able to more accurately determine what's going on when these objects collide. But most importantly, we might be able to finally determine what happens to the information. Because without being able to preserve the information that falls into the black hole, it actually violates quite a lot of laws of physics. But one day we'll be able to explain all of this, and thanks to this paper we now have a very good technique on how to measure the overtones of the collisions, and these overtones will provide us with a lot of information about what's really happening once these black holes collide. And although this doesn't necessarily prove Stephen Hawking completely wrong, because one of his ideas was that maybe the information is also released through the so-called Hawking radiation, which we believe does exist, and you can definitely learn more about this in one of the videos I made previously somewhere above my head. But this particular discovery, or this particular paper, definitely suggests to us that black holes don't really have the so-called hair. They're more or less identical, and if they do store information, it's stored in some other unusual way. Well, anyway, that's all I wanted to mention in this video. Check out the paper in the description below, and once we learn more about black holes and black hole collisions, we'll definitely talk about this in one of the future videos. Also, if you'd like to see how many different black hole and neutron star collisions we've discovered in the last few, well actually, days and weeks, because they've been happening pretty regularly, you can check out this website right here, the publicly available GRACE database. Here, every single detection is almost instantly available to us, and you can even see what we think it is. Like for example, right here, here's another black hole collision, and there's a 99% chance that we've discovered another one in September of 2019. Hello wonderful person, this is Anton, and this right here is a black hole. Today we're talking about yet another unusual discovery about these beautiful unusual giants. Now you may have noticed that in the last 2 years, specifically in the last few months even, there were a lot of videos that I made that were about black holes. And that's actually because we are now in the golden age of the black holes. We're basically in the golden age of discovery, understanding, trying to find them, and of course take pictures of them. Some of the biggest breakthroughs in black hole studies were in the last few months alone. And one of the reasons why it's just happening now is, well, because our instruments got much better. And also because a lot more people became interested in studying them and joined various teams trying to analyze and learn more about them. And so today we're going to be talking about a discovery of a type of a black hole that we never really knew existed. Now, when it comes to detecting black holes, we've seen quite a lot of these so-called solar mass black holes. This is a very good example. This is known as Cygnus X1. And this black hole orbits a very giant star that is somewhere right there in the back. You'll see it in a few seconds. And basically the reason we actually can even see this black hole, and in this simulation it's a pretty accurate representation of how bright and powerful it is because this black hole is stealing the material from the star, and as this material falls onto the black hole, it creates the accretion disk, which then creates the very powerful jets that emanate from the black hole that can be detected from planet Earth. So these are called stellar mass black holes, and normally their mass is anywhere from like 5 to maybe 12 to maybe 15 masses of the Sun. However, in the last few years, the LIGO detector has also been able to see quite a lot of other black holes of different masses, with the binary black hole that was detected first being roughly around 30 masses of the Sun each. So in that sense, we understand that there are a lot of different discrepancies in masses of black holes. On the opposite side of the spectrum, we also have these beautiful giants known as supermassive black holes. That's the one in the middle of our own galaxy, Sagittarius A star. And one of the ways we know about their existence is by literally observing the motions of stars and seeing that they orbit something extremely massive in the middle. Here's what it all looks like in the middle of our own galaxy. Then somewhere in between these two black holes, we also possibly have intermediate-sized black holes, which are still a little bit more elusive. We've only seen partial hints of their existence in our galaxy, but we do think that they're somewhere out there. These are black holes that are normally several thousands masses of the Sun, which is still a lot less massive than these black holes, which are usually in millions or billions masses of the Sun. So in that sense, there is quite a wide range of black holes we've discovered and have been able to observe. So what is this new discovery then? Well, this discovery comes from the data of this experiment right here known as Apogee, which has studied the light or the spectra from around 100,000 different stars in our galaxy, and the scientists behind this paper were looking at something known as the Doppler shift, where the spectrum suddenly changes and becomes either a little bit more blue or a little bit more red. NASA actually made this beautiful simulation that you see right here that explains how they often use this for essentially finding planets. Here, by seeing the star increase and decrease in speed, you can actually see its light change from being a little bit more blue to being a little bit more red. And all of this is caused by the massive planet that sort of increases the star's speed or decreases the speed. So in other words, we can usually very easily see a star that's orbiting something, or a planet that orbits a star, assuming this planet is very massive and can actually increase the velocity of the star. And so by using the data from Apogee and by using the technique you see right here, the scientists behind this study discovered something really unusual around a very large red giant. The star, whose name you can see right here, whose name I'm also not going to try to pronounce because there's just way too many numbers, essentially looks something like this if you were to look at it with a telescope. And in this particular location, they discovered that the unusual red giant was actually orbiting something invisible in the middle. And they knew that because the star itself seems to accelerate by roughly around 3 kilometers per second every single day. And it also seems to actually have periodic changes every 82 days. Suggesting, of course, that there's a black hole in the middle and the star orbits this black hole every 82 days, and star's velocity changes by 3 kilometers per second every single day. And although discovering a black hole and a star with orbit around one another is not really a big deal, the big deal here is the mass of the black hole. The mass seems to be really small. It's only about 3.3 masses of the Sun, which is way too small compared to any other black hole we've seen so far, but also a little bit too big to be a neutron star, so we don't think it's a neutron star. In other words, they may have discovered the smallest black hole ever found, which of course doesn't really have the same ring as the biggest black hole in the universe, which I've talked about on the channel in one of the previous videos, but it is still a really cool discovery. Now the star itself is actually nothing special. It's what's known as a K-type star, so it's a little bit less massive than our own Sun, but it's also in its later stages where it's already becoming or has become a very large red giant. Our Sun will obviously do that too one day, but not anytime soon. The initial calculations suggest that the mass here is maybe about 80% of the mass of the Sun, but all of the observations of course suggest that this star, despite its relatively high mass, is definitely orbiting an empty point of space. It's probably not a neutron star, it's very likely the smallest black hole. And the thing is, we don't really know how to explain the existence of this black hole. So it could be a completely new type of black holes, although it's possible that it was created through some kind of a supernova that happened many years ago when the star that you see here was much younger and a lot smaller. At the same time, the scientists behind this paper also proposed that, well, maybe the way that this black hole was generated was not through an explosion, but through just direct transition of an old dying star into, well, just this. It basically turned into a black hole without any other unnecessary steps. So there's still no actual clear explanation to how this exists, but it seems that it definitely exists. And this of course will also help us explain one day how is it that some stars do become neutron stars, some stars just explode, and some stars turn into black holes. So this discovery will bring a new understanding to this unusual idea of these unusual objects that we're now very thoroughly studying in a lot of detail. Now I'm actually really excited to see the follow-ups to this paper because it's a pretty big discovery, and this year has been pretty good for black holes in general. Hello wonderful person, this is Anton, and in this video we're going to be talking about the paper that discusses an ultra-massive black hole at a distance of about 700 million light years away from our galaxy and from our planet Earth. This particular black hole is unusual in that it's most likely one of the most massive, if not the most massive, black holes ever discovered. So when it comes to black holes, specifically stellar-sized black holes, or even so-called supermassive black holes, we understand how they work for the most part. But there's one type of a black hole we don't really get, and we are not really sure how they were formed. These so-called ultra-massive black holes that are usually so tremendously massive and large that they're basically a size of a typical star system. And so by looking at a region of space that's not really that well studied, these scientists were able to discover one galaxy that has basically a tremendously large ultramassive black hole that might be also the closest one to us, at a distance of around 700 million light years away from us. This would be the closest such black hole to us and would definitely require further observation. It's located in this region right here, known as Abell 85. The nebula you see is actually much closer to us, it's sort of in front of the image, but we're looking at the galactic cluster, which is of course when you have several different galaxies gravitationally bound to each other and sort of moving in the same direction. The closest cluster to us is of course the Virgo cluster. This one is much farther away. And here we have over 200 different galaxies, but the brightest one is known as Holmberg 15. This is the galaxy's image, and unfortunately that's really one of the few images out there. That's the only one I was able to find. But the scientists behind the paper right here, that you can also find in the description below, were able to very accurately discover the mass of that central black hole. And they did so by analyzing the luminosity of the central region and realizing that the closer you get to the center, the brighter and brighter things get, to the point where they're unexplainably bright. So bright, as a matter of fact, that the only explanation is a tremendously large and massive body that's producing all of this luminosity. And so by using the so-called Very Large Telescope from the European Southern Observatory, they were able to then calculate the mass to about 40 billion masses of the Sun. Now that is roughly around 5,000 times more massive than the one in the middle of our own galaxy, Sagittarius A star, and it's also approximately 7 to 8 times more massive than the very famous M87 black hole, whose photo is probably one of the most famous photos of 2019. So that particular black hole, even though it is massive, is not as exciting as the Holmberg 15A star, as it's now known, because it's essentially one of the closest record holders to our galaxy. 40 billion masses of the Sun is as close to the highest number we've ever discovered, and even that number is still not entirely confirmed. Some scientists even suggested that the black hole here might be as massive as 150 billion masses of the Sun. So this number will definitely need to be confirmed in the future, but what we know for sure is that it's at least 40 billion, and it's right there in the middle, and it's the closest one. And although that's still a little bit smaller than the largest ever black hole we discovered, which is TON 618, this one is about 66 billion masses of the Sun. It's still very impressive, especially because this is a quasar that's really far away from us. However, this is not a quasar, it's a typical galaxy, a regular galaxy, with an unexplainably massive and super large black hole in the middle, and also possibly even more massive than we currently calculated. And to help you visualize all of this, we're going to place this black hole right here in our own solar system just to see how far it reaches. There is Earth right there, that's Venus, there's Mars. Let's place it basically right here next to our Sun. But we're going to start by placing Sagittarius A star, the supermassive black hole, in the middle of our own galaxy. I think it's actually a little bit easier to see all this with a different background. So there's our Sun, it's a very small spot. There's Sagittarius A star. Here is planet Earth and its orbit. And we're now going to kind of zoom out just to see how large things will get when we increase the mass of that black hole to the mass of the newly discovered Holmberg 15A star. So here we really need to move farther back, and there you go. Its radius is around 790 astronomical units, meaning that it would swallow pretty much everything in our solar system, with maybe Sedna kind of being left behind. We can try to place the Sun a little bit farther away, with Earth being right here, and the distance between the Sun and the Earth here is just 1 astronomical unit, and this is how tremendously large this black hole is. So this right now is probably one of the more mysterious and more interesting giants we've discovered, and one of the reasons it's so mysterious is because we don't really understand how such a massive black hole could have been created. The current explanation in the paper is that it was the result of a collision of two ultramassive black holes from two different galaxies that collided sometime a few billion years ago. And although galaxies collide all the time and such explanation does make sense, it still doesn't explain how it could create such a tremendously large black hole. Specifically, how all of this resulted in what we're observing, a very, very bright, very active central region. And because, interestingly, for this particular galaxy, the halo of dark matter seems to orbit a lot faster than it should, with the velocity of about 750 kilometers per second, the scientists, some other scientists, assume that the mass of the black hole must be even higher. They suggested the values that are about 4 times or even more than 4 times higher than in this particular paper. In other words, whatever is happening in this galaxy is kind of a mystery, and it definitely needs to be investigated further. And even the scientists in this paper were quite surprised to find out that the expected value for this black hole is about 9 times less massive than what they've discovered. So we didn't really expect to find anything so massive right there in the middle. But since for this paper the researchers used a very well-known correlation between the X-ray radiation and also microwave radiation and of course the total mass of the central bulge, it's possible that maybe something else is causing this. Maybe there is some kind of a event or some kind of activity behind all of this cloud of dust and stars that we just are not familiar with yet. It is possible that it's a black hole, but it's also possible that it's something we don't really understand. Because for one, we really don't understand how such a tremendously massive black hole can coexist with this galaxy. How can it actually exist in there and not basically swallow everything? And how can such a tremendously massive object still maintain a relatively quiet galaxy that we see in the middle of the galactic cluster Abell 85? So in that sense, there are still quite a lot of mysteries, but it really just means we really don't understand these ultramassive black holes at all. For one, we expect them to swallow so much material and so much dust that they should technically completely prevent a galaxy from forming any stars. They should totally and entirely reduce a galaxy to a very quiet, very dim object. But this galaxy is not dim, it's super bright, and there seems to be a lot of stuff going on in the middle. So ultramassive galaxies are definitely a huge mystery to us. And by the way, the mass of this black hole that we just discovered is very similar to the mass of the black hole in the middle of the largest galaxy ever discovered. The black hole in the middle of Holmberg 15A seems to be pretty much around the same mass and size as the black hole in IC 1101, which is a galaxy that's ridiculously large and way larger than Holmberg 15A is. So we're not entirely sure how two completely different galaxies can have two relatively similar black holes in the middle. But if the size and mass of Holmberg 15A is confirmed, or even if we are able to recalculate it to be even higher, it would definitely make this in top 3 most massive black holes ever discovered and ever confirmed. At 40 billion masses of the Sun, it's right behind IC 1101 black hole, but if its mass is higher, it might even get to the top spot. And if the scientists behind this paper are correct, it makes Holmberg 15A star the closest ultramassive black hole in the local universe detected by using Earth telescopes and observatories. In other words, it's the closest, most massive neighbor that we have. But until someone else can confirm these discoveries and these calculations, we're going to have to err on the side of caution, mostly because when it comes to black holes, there's still a lot of stuff we just don't really know. Hello wonderful person, this is Anton, and in this video we're going to be talking about yet another mystery of the black holes. But this time we may have a solution to one of the biggest mysteries: how certain black holes seem to get so extremely large, much larger than they should be. Now, in the last few years, we've discovered quite a lot of really interesting black holes, and more specifically, super and ultramassive black holes, and we were obviously even able to take a very beautiful picture of one of the nearby ones, the mysterious Poehi inside the galaxy known as M87, with the actual stream right here that you see being formed by the very powerful black hole itself. But despite our understanding of what usually happens around these giants and us being able to even see what happens around the black hole Sagittarius A star, which is the central black hole in our own galaxy, there are still a lot of mysteries. And more specifically, we've actually discovered some black holes that are just too big, too massive. Even this right here is a little bit more massive than it should be. In terms of the actual masses, it's roughly around 6 billion masses of the Sun, which is several thousand times higher than the Sagittarius A star black hole that you see right here. Just to give you an actual visual comparison, let's take our solar system and first place the Sagittarius A star, that's our own black hole, in the center with the Sun for comparison here, so you can see how big it is. And now let's place Poehi from the M87 galaxy, for which we actually have to zoom out quite a lot here because it's going to swallow pretty much most of the solar system. And although it's a little bit difficult to see its true size here, if I change the background, you'll start seeing it a little bit easier. So basically here you can kind of see the outlines of the event horizon of this tremendously large and powerful black hole. And this right here is the orbit of Neptune. But this is not even close to the largest and the most massive black hole we've discovered. There are some that are even bigger than this. About a year ago, I've made a video about this beautiful black hole, Holmberg 15A, and also there's another older video about TON 618. Both are considered to be some of the largest, but possibly not really the largest yet, because we're yet to discover more. These are maybe about 10 times larger than what you just saw with the Poehi black hole, meaning that they'll cover this entire area. But here's the problem. We don't really understand how such a tremendously massive black hole can form. With Sagittarius A star, which is somewhere right there in the center of the solar system, it's a little bit easier to explain because those masses are something we do expect for massive black holes to have. But this is another story. How can a black hole get so tremendously massive, especially with some other galaxies we've discovered that seem to have these black holes, like this one right here, for example, much earlier in the creation of the universe. In other words, these super large and tremendously powerful black holes existed very early on in the creation of the universe and were already really massive only a few billion years after the universe came to be. So this is something that we're just having trouble explaining, and we don't really know how this happened. But one of the possible solutions to how these black holes became so large and so massive comes from a recent discovery from a nearby Seiffert galaxy known as M77 or Messier 77. Just like M87, this was originally discovered by the French astronomer Charles Messier, who basically classified 110 different objects using his by then pretty advanced telescope, all of which was done roughly around 300 years ago. So this was one of these objects, this is M77, and we refer to these objects as Seiffert galaxies because essentially it's literally a quasar. It's a very active galactic nuclei galaxy. It has a lot of energy generated in the center. The actual black hole is consuming a lot of matter and spewing out a lot of actual gas and a lot of energy. And because of this, it also sometimes prevents other stars from forming. But unlike other black holes, specifically ultramassive black holes, this one is still growing, and it's growing really fast. This is maybe about 4 times more massive than the one in the middle of our own galaxy, but the main reason we call these galaxies Seiffert galaxies and not quasars is because in Seiffert galaxies we actually also see the galactic shapes as well. We see the arms, we see the star formations and globular clusters. So basically a typical quasar is just an extremely bright and powerful shape, and usually we're actually seeing the emissions, we don't really see the galactic shapes. But when these emissions happen a lot closer to us, and especially if they're not really pointing directly at us, we then refer to these galaxies as Seiffert galaxies. And so one of the first described Seiffert galaxies was the beautiful galaxy M77 that's about the same distance away from us as M87, so just a little bit closer actually, it's 47 million light years away from us. But because it's a Seiffert galaxy, it's actually really interesting to us because it allows us to study these unusual quasars by studying something that's relatively close to us. And the most important part about this galaxy is that it seems to be a somewhat inactive quasar. In other words, it's not super active just yet, even though it's already throwing out a lot of gas at something like 500 kilometers per second. But there is still star formation happening here, so it's not super active. But by studying this unusual black hole in a little bit more detail and by looking at it using radio waves, because basically the black hole itself is covered by the gas, so you can't really see it in visual light, the scientist behind this paper right here discovered a potential reason explaining how so many different black holes grow so big so quick. When they looked at the center of this galaxy in a little bit more detail, they realized that first of all, obviously, like so many other black holes, it has an actual accretion disk and a lot of other material roughly up to about 4 light years away from the black hole orbits in one direction. But to their surprise, once they looked at the distance from 4 to 22 light years, they discovered that the actual disk was orbiting in a completely other direction. In other words, the closest disk was orbiting this way, but the farther disk was orbiting the other way. And this gave the scientists a really good explanation for how one day this black hole is going to turn really massive as well. At some point, the two disks that are orbiting in completely opposite directions will very likely start sort of colliding with one another, and all of the particles as they collide will lose all the velocity and eventually start slowly falling into the black hole, making it grow in size and essentially increasing the actual power of the black hole, turning it into a very powerful quasar or very powerful Seiffert galaxy. So all of this matter, as it sort of combines with the black hole, will very likely add a tremendous amount of mass, turning it into one of the biggest black holes in the vicinity. And because the scientists were able to find at least one example of this rotation and counter-rotation disk inside of a typical galaxy, it's very likely that these examples exist pretty much everywhere across the universe. And this is actually a very solid explanation to how a typical black hole grows in size and in mass suddenly and dramatically. This is actually a very good explanation and technically is the best explanation we have right now for how so many massive and extremely large black holes seem to exist early on in the existence of the universe. But I guess the next question is, so how exactly did this galaxy acquire a disk that spins in one way and another disk that spins in the opposite way? How is that even possible? Because technically these counter rotations have only been detected at much larger distances away from galaxies, and normally these are formed when a galaxy collides with another galaxy, and inside of these galaxies it's very common to find very unusual motion that's otherwise hard to find in a typical galaxy. So if this is what happened here as well, it must have been a collision that happened between a large spiral galaxy like M77 and some sort of a smaller galaxy, very likely similar to, for example, our own satellite galaxy Magellanic Cloud, that will also one day collide with the Milky Way. Now here, if we try to simulate this, you'll notice that the collision might not actually create these similar effects, but as you can see, the actual smaller galaxy gets absorbed inside the center of the galaxy, and there it could technically create this unusual accretion disk that we observed, which is exactly what the scientists observed in M77. So this observation does kind of provide at least one explanation for the mystery of these so-called ultramassive black holes existing very early in the universe. But it doesn't really tell us how all of this happened. I mean, galactic collision is one way. There's maybe something else that happened that caused this particular galaxy to have these two unusually shaped disks that we've observed, but it also might have created a completely new mystery as well. For now, the best thing that we can do is actually to keep looking at new galaxies and try to see if we can find these particular effects somewhere else out there, which would definitely suggest that this is a common phenomenon that does happen in many different galaxies. And it would also explain how these tremendously massive black holes can form so quickly and with such tremendous ferocity. Now, what's interesting is that obviously this also suggests to us that at some point our neighbor M77 is going to become really powerful. Now, will this have any effect on the Milky Way, specifically on planet Earth? That we don't really know. Right now it's still quite powerful, but not powerful enough for us to actually feel any effects from it. But if this quasar becomes really strong, and if the astrophysical jet starts pointing at us, that could be a problem. The mass extinction type of problem. Because a typical quasar and the astrophysical jets produced by these quasars, if pointing at a certain planet, could totally strip that planet of atmosphere and destroy any life on that planet. Now the chance of that happening is actually pretty low, but it's always there. Anyway, it's not going to happen anytime soon though, and it will probably take a few thousand years before we reach the point where M77 does become quite active, but we're talking thousands of years, not millions and not billions. Humanity might still be around, and if so, we need to be ready if it decides to point in our direction. Now, it's very unlikely, but you never know. Anyway, on that note, once we learn more about this unusual phenomenon and discover why exactly M77 has such an unusual disk that orbits in a different direction, we'll come back and talk about this more. Hello wonderful person, this is Anton, and today we're going to be talking about supermassive black holes once again. And more specifically, we're going to discuss planets around these objects. So this right here is a simulation with a black hole, very massive black hole, and a planet nearby. And we've actually discussed the idea of having various planets, including habitable planets around black holes, in one of the previous videos. But today we're going to talk about the idea of planets forming around black holes and actually becoming their own sort of objects, without any stars, without anything else in the vicinity. And it's a study that I recently discovered completely by accident, and you can also find it in the description below. This study doesn't really talk much about the nearby or the close regions of a black hole, specifically the regions that you see right here. And it doesn't really talk about the accretion disk or any other regions that we normally talk about. It talks about the so-called circumnuclear region, or the so-called circumnuclear disk that you can kind of see right here. And we believe that our black hole has it as well, we just don't really see it because of the perspective from which we're looking at our own black hole. But we know that these disks exist, and it's actually one of the reasons why the M87 black hole, where we're zooming in right now, is so difficult to see. It's surrounded by this tremendously large disk of dust that's covering the black hole, and you can only really see the black hole through the radio waves that pass through the dust quite easily. Now, to help you visualize some of this, let's try to recreate some smaller parts here in Universe Sandbox, just so you can see what we're talking about. So here's a black hole. This is Sagittarius A star, the one in the middle of our own galaxy, and it's surrounded by the accretion disk. This is a much smaller version of the typical accretion disk, just to represent what all of this looks like. This is the matter that slowly orbits around the black hole and basically makes its way toward the center. And then at a much larger distance, usually very far away, sometimes even several hundred light years away from here, there is another very large formation known as the circumnuclear disk. Now right now it's very difficult to see it, but as I add more parts to it, you'll realize that it's essentially this extremely large torus shape that is literally hiding the black hole because of all of this dust that sort of orbits around the black hole and prevents the light from escaping it. And this very large shape, this torus shape that has formed through this dust orbiting around the black hole, that's literally what we refer to as the circumnuclear disk. Now, the shape and the size always differs, but we know that these objects are much larger around active galaxies, specifically galaxies with active galactic nuclei. So if the black hole in the middle is very active and produces a lot of energy, spewing out a lot of gas in the process, this usually results in a much larger circumnuclear disk that is then a lot better at literally hiding the black hole. Which is why M87 is so difficult to see, because the circumnuclear disk there is very large. But in a typical, somewhat active galactic nuclei, specifically in a galaxy that's not really a quasar, not a very bright object, but it does have activity in the middle, there's usually enough dust here to form a disk that's around 300 to 400 light years across, and usually the mass of this disk is around 10% of the mass of the black hole. So hypothetically speaking, for our black hole, this means that it would be about 400 to maybe 500,000 masses of the Sun, all concentrated in this relatively large disk. Now some parts here take about 1,000,000 years to orbit, some parts will take 100 million years to orbit. So the actual orbital speed and the actual interaction between particles is very minute and very small. But sometimes these galaxies stay like this for a very long time. And this is what the scientists behind this paper decided to try to calculate and study. They realized that these tiny particles, these little particles that you see here, each of them eventually is going to start mixing together and eventually form bigger and bigger and bigger shapes. And at some point, this can become large enough to literally start forming planets. Now, they tried to do the simulations of this and try to calculate how long this would take, and they realized that this is a very slow process. But they also realized that it's quite possible because of the conditions that are created so far away from a black hole where it's no longer really energetic, but also where there's enough material for all of this to start coming together. Now, this object right here is about 100 meters or about 300 feet in radius, and they believe that such an object would potentially be produced within the time of AGN. In other words, for this black hole in the middle to be active, it needs about maybe 10 to roughly around 100 million years. And during this time, this could be produced. Such object could definitely be made and then have enough mass to start attracting other objects, to literally grow in size quite exponentially, similarly to how planets grow from a typical circumplanetary disk that we've observed in many different systems out there. Now, the only main difference here, of course, is that it's a much slower process. There is no star in the middle to kind of start influencing things, but instead there's a black hole. And at the same time, there's probably very little interaction between objects and very little collisions or any other disturbances. In other words, it's a very slow process, but it's a very methodical process, and it's probably quite good at producing really large, really massive planets. Depending, of course, on what happens to all of this gas with time, and whether this gas can continue to grow and then maybe even become a star. Now, let's actually see if we can create a tiny planet here using the material that is orbiting this black hole, and let's maybe see if it actually turns into a star as well. But a very important reminder from this paper is that this is a really slow process. So essentially, after about 100 million years, you would expect to see maybe a planetary size object, or at least a protoplanetary size object. And then maybe within about 100 more million years, you would start seeing quite a lot of relatively large moon-like or possibly even planet-sized objects, but obviously all of them quite far away from one another. Now, the dust here, for the most part, is probably only hydrogen and helium, so it's very likely that a lot of these objects would probably end up being some sort of gas giants, or at least objects similar to a typical gas giant. And obviously, as they grow larger and larger, there's also a chance for them to become stars. And although the theory behind this is actually pretty solid, and there's definitely a lot of material out there very close to these black holes to produce these objects, the more difficult part for us would be to actually detect these objects, because planets are relatively hard to see, especially so close to a black hole. And so it's very likely we're not going to be able to see these planets unless, of course, they do actually turn into an object like a brown dwarf, or even better, some sort of a star, a red dwarf. If we actually do detect a young red dwarf somewhere in the vicinity of a black hole, specifically within about 300 or so light years away from it, and it's a star that was just born, it's probably something that was created in this way, and this would definitely be a very solid proof of this particular hypothesis. But for now, it's unfortunately only a hypothesis based on simulations and I guess based on relatively solid math and understanding of the galaxy. But even though in this particular simulation this star is relatively close to the black hole, and all of the planets that have been created are also very close, we believe that for a typical supermassive black hole, this can only start happening on the outskirts or past the outskirts of the so-called snow line. And for a black hole like this one, this snow line is really far away. And let me show you how far away it is. It is at least 5 light years away from the center, which is basically somewhere over here. It's actually even more than that because the black hole we're using is more massive. So this is roughly where the so-called snow line is, and past that we could potentially produce these planets. But within this radius, it's just not really possible because the black hole is too energetic and produces way too many emissions for the circumnuclear disk to produce anything that's capable of creating planets or of course stars. And what's more, once the black hole is no longer active, similar to the black hole in the middle of our own galaxy, we don't really know what happens. We believe that this gas does sort of eventually dissipate and probably escape into the rest of the galaxy, traveling across the galaxy, possibly combining with other dust clouds, and maybe even falling onto planets like planet Earth. But we don't think that it becomes a planet or a star by itself. As a matter of fact, we think that maybe some of this gas escapes the galaxy completely and then becomes the so-called intergalactic dust, especially if this gas moves really fast. But for now we don't really know. We know that the dust interaction and also the particle interaction within galaxies and between galaxies is very complex. We're still learning quite a lot about it. As a matter of fact, I'm currently making a video about the intergalactic dust that's going to come out really soon. Or maybe it has already come out if you're watching this in the future. But for now, that's really all I wanted to mention in this video, and basically, just to give an idea, we think that in this region right here, roughly around 200 to maybe 300 light years away from a black hole, we could have planets form completely by themselves, especially if the galaxy is not too active, but also not too quiet. Specifically galaxies like the beautiful galaxy Centaurus A that you see right here, that's one of the most beautiful galaxies out there, and is basically the closest such galaxy to us. Here, there might be planets forming. And if we actually have a powerful enough radio telescope, specifically the telescope that allowed us to take a picture of M87 black hole, we might be able to use similar technology to look around the black hole and discover radio pulses coming from these planets. But this is not something we'll be doing anytime soon, and it will probably take a few years before such mission will even begin. For now though, it's definitely a really interesting idea, and if one day we discover a planet somewhere on the outskirts of a black hole, it's probably going to be around this galaxy right here. Hello wonderful person, this is Anton, and in this video we're going to be once again talking about black holes. We're going to return to M87, known as Powahii, and we're also going to talk about a relatively recent paper that was published only a few days from when I'm making this video, talking about another discovery coming from this region about this particular black hole based on the analysis of the data. And the scientists behind this paper that you see on the screen right now, and also that you can find in the description below, were able to calculate the spin of this black hole. In other words, they took the data from the Event Horizon Telescope and were able to calculate how this particular black hole is spinning and how much energy it produces with its rotation. And that of course is something that is quite incredible when you think about it. So let's talk a little bit more about this, and let's start with the idea of, well, so how did they actually find out how much this black hole is spinning? This is actually not that black hole, this is just a random black hole I've discovered through procedural generation in Space Engine, because a more realistic image of Powahii, also known as M87 ultramassive black hole, would be something like this. It has ridiculously powerful astrophysical jets, it also has a relatively large and very powerful accretion disk, but most importantly is that it's really massive. Its radius currently is estimated at approximately 120 astronomical units, which is 120 times the distance of Earth to the Sun. In other words, if you were to place it in the middle of our own solar system, as I've done in one of the previous videos, it would swallow everything, including the Voyager probes that are still trying to leave the solar system. But in order for us to see the actual black hole itself, we need to dim things a little bit, we need to really kind of remove the visual light here, just like as the telescopes did, and in some sense focus on the invisible light to our eyes, the radio waves that are produced by the interaction of various matter here. So first of all, the spin of the black hole has nothing to do with the actual spinning of the accretion disk. As a matter of fact, this is normally the biggest confusion people have, is that they imagine the black hole spinning and relate it to the actual accretion disk. So let me try to explain what's happening here by looking at this black hole right here. So if we look closely, we'll see that the accretion disk is spinning and matter slowly falls into the black hole. This is due to the actual gravity of the black hole and is not really related to the spinning black hole itself. All black holes in the universe have at least three major components. One of them is charge, which is not going to be mentioned here because we don't really know what the charge of this black hole is. One of them is mass, and we've established the mass of this at 6.5 billion masses of the sun. But one of them is spin, and that's related to the actual black hole itself spinning and thus kind of dragging the space-time itself around it. Now this is something very, very difficult to imagine. As a matter of fact, it's almost impossible to imagine without visual simulations. And here's one where you do have a fastly spinning black hole that actually creates a very unusual effect around itself. And as it drags the space-time around it, what happens is that it acquires this unusual area known as the ergosphere, which creates a phenomenon that I've described in one of the previous videos where I talked about the halo drive. In short, just to kind of give you a brief summary of this, if you were to enter this area, you can leave this area with more energy than you entered, thus getting acceleration in a sense. Or in case of, for example, light, if you were to shoot a laser into this region, this laser can be returned to you with more energy than you've given it. So in other words, it creates a kind of a free energy source. But of course it's not free because the energy is being stolen from the black hole itself. You can check out the video about this somewhere above my head. But the idea here is that it also creates a much more stable region that you can orbit around because the black hole is spinning. Now, another really crazy effect that spinning black holes create comes from the movie Interstellar, but that movie took it a little bit to the extreme. Although I'm actually going to recommend an amazing analysis about this, including some scientific explanations without really any difficult math, from a really famous scientist, Jean-Pierre Luminet. Jean-Pierre Luminet is the first ever person to create a simulation of a black hole. This is actually made before the computers were available, and he created this using a punch card. And this is back in the 70s, I believe. And interestingly, he's the one that analyzed the movie and actually talks very thoroughly about the science in it, in this paper that you can also find in the description below, where he also discusses the idea of a spinning black hole, and it does kind of describe the effects of spinning black holes in more detail. But in summary, you do get ridiculous time dilation effects, and the space-time itself will actually be stretched so much that things don't really behave in the same way anymore. And so we know that the Poway black hole, the M87 ultramassive black hole, also spins a lot. As a matter of fact, its spin, as calculated by these European scientists in this paper right here, is approximately 0.9, which refers to roughly around 90% of the limit of a spinning black hole. Obviously, the black hole cannot spin faster than the speed of light because at this point it would just not exist anymore. So the spin of 1 represents that. 1 is the maximum you can have. This black hole has a spin of 0.9, which essentially gives it a tremendous amount of energy that it generates through the actual spinning power. And the energy it creates is so difficult to explain without using unusual scientific terms that I'm going to have trouble here. It spins with energy of about 10 trillion foes. A single foe is usually used to describe supernova. A typical supernova produces so much energy that it's difficult to explain it in earthly terms. We cannot use joules, well, I guess we can, but it's just a very big number. So instead, the scientists created a term known as foe, which I guess is more easier to explain if you look at our sun. Throughout its whole lifetime, our sun will produce approximately 1.2 foe of energy. That's equivalent to just a little bit under one single supernova explosion. Normally supernova are around 1 foe. This ridiculous black hole spins with so much energy that it produces 10 trillion foe. It's literally equivalent to billions of years of production of energy in the entire Milky Way. Our galaxy itself is not producing enough energy compared to just the spin of this ridiculous black hole. But I guess the question is, so how did they even find this spin? Well, because it's bending space-time so much and because it has so much spinning power, it actually influences the light that's leaving the vicinity of this black hole. So when EHT, or Event Horizon Telescope, received the light that was coming from here, it was literally like a vortex of light that was twisted and warped into a very unusual shape. And this is often referred to as the orbital angular momentum, which was actually measurable when the light was detected from this black hole. And because the black hole is warping space-time around it, they were actually able to use the region around the black hole known as the Einstein's ring. That's a little bit easier to see around this black hole that doesn't have an accretion disk. So this ring that you see right there, that's the Einstein's ring, and it kind of warps the light around itself due to various effects from the theory of relativity. And they were able to observe this and realize that it was highly twisted. It had a very, very high vorticity. And using this vorticity, they were able to establish the actual spin of the black hole. They were also able to confirm that it has an inclination of about 17 degrees and that it also spins clockwise toward us. But more specifically, they also realized that this black hole has a spinning power that's about 10 to the power of 28 times more than the spinning of Earth. Now, I just wanted to include that number just to show you how ridiculous the power of this black hole is. But yeah, it's insane. It's more powerful than individual galaxies. It's also more powerful than quasars, which are the most distant galaxies in the universe that are so powerful that we can see their light from Earth. And so that black hole has more energy in its spin than quasars do in radiating energy toward us. That's very impressive. But because of its ridiculous size, it also doesn't mean that it is visibly spinning. As a matter of fact, the single rotation here would take it about 100 hours because of its sheer size. Assuming that they are correct in their analysis of the actual size of the black hole, it's still not going to be spinning really fast like some of the smaller black holes. But we're actually going to talk about the fastest spinning black hole in another video that's going to come out sometime soon. Hello wonderful person, this is Anton, and can you guess what you're looking at? This of course is the central part of our galaxy, and the little part in the middle is the supermassive black hole known as Sagittarius A star. Now in this video we're going to be talking about a new study that was able to use a very unique, very new method to calculate the mass of another really massive black hole somewhere out there in the universe, and today we'll talk about how they did it and what they've discovered. Now when it comes to measuring masses of black holes, there are different methods. And the most obvious method is right here by looking at the orbits of stars nearby. This is kind of how we've discovered the mass of our own black hole. And so here, by looking at stars long enough, you can usually see how long it takes for them to orbit this imaginary point in the middle. And using this, you can then calculate the approximate mass of the black hole. This is how we discovered that the one in the middle of our own galaxy is about 4.3 million masses of the Sun. There are also some other methods that use, for example, the motion of gas around the galaxy, and in one case we can usually get a very precise measurement of the mass of a black hole by looking at the emissions of what's known as masers, basically like lasers but in microwave frequency. These masers are emitted by the interaction of the actual energy coming from the black hole and the gas nearby, and using various parameters we can normally very accurately calculate what's in the middle. But maser calculation doesn't work for all galaxies because not all of them produce them. As a matter of fact, it's very rare that we find a galaxy that produces these unusual emissions. Mostly spiral galaxies have them, and most of the other irregular or elliptical galaxies don't produce any masers whatsoever. And so if I wanted to calculate a mass of a black hole in, let's just say, a different galaxy like this one right here, M101, or any of the other well-known galaxies, specifically the ones that don't really have a very pronounced spiral, like a typical elliptical galaxy, I would not really have a good method, until now. And so the scientists that published their paper very recently were able to calculate with extreme precision the mass of a black hole that's roughly around 130 light years away from us in a very massive galaxy known as NGC 3258. You can check out this paper in the description below, but the idea here is that they found a way to measure the velocity of the gas ring around the black hole, and by using the measured velocity as well as the differences in velocity across the disk, they were able to very accurately predict what's in the middle, basically what is this gas orbiting around. And just to give you an idea of actual sizes involved in this disk, I mean, it does look like a typical solar system, but it's really not. Here, 100 parsec is about 326 light years, so that is about 1,000 light years across. That's a pretty large disk. And so by using the data from ALMA Observatory, the scientists were then able to very accurately determine that the speed on the outskirts here was roughly around 280 km per second, while the speed closer to the actual center was about 400 to maybe even 500 km per second. And by using the actual shape of the disk and also by using the total mass of other objects like stars and all of the dust itself, the scientists were able to estimate the mass of the black hole at 2.25 billion masses of the Sun, which is roughly around close to 1,000 times more massive than the one in the middle of our own galaxy, suggesting that this is what's known as an ultramassive black hole. It's also roughly around half the size of the super famous M87 black hole, although the mass measurements here are actually not as accurate as the mass measurements for NGC 3258. The actual measurement of the black hole right there in the middle have about 99% accuracy with only about 12% discrepancy based on the distance. We're not entirely sure how far away this galaxy really is, but the actual measurements are super precise. And the way that all of this was achieved was by trying to calculate the velocity of carbon monoxide gas that's present in this really large disk of cold gas. So essentially what they looked at was the actual Doppler effect, Doppler shift, basically the blue shift and the red shift of the velocity of the gas. And by measuring carbon monoxide velocity, they were able to determine that here it's moving around 280 kilometers per second. Closer to the black hole, it moves around 400 kilometers per second. And they had very precise and very detailed analysis of the actual change in velocity that you can discover in the paper in the description below. And if we were to look at this galaxy from our planet Earth, we would realize how tiny it actually is in the night skies. So it's somewhere right there, and we really need to zoom in here with our telescope to actually start seeing the galaxy itself. So we were able to very precisely calculate the mass of a tiny dot right there in the middle by looking at a tiny disk orbiting around this tiny dot. And today we know that approximately 10% of all of these galaxies, very similar to this one, usually have these types of disks. These are basically cold gas disks that orbit around the central region. So we can now use this technique to very accurately calculate the mass of the black holes in the middle of a lot of different galaxies out there and possibly discover something even larger and even more unusual. And although it's quite unlikely that we'll be taking an actual picture of this black hole, even though it is somewhat similar to M87, it's still quite interesting to find out that we now have a new technique that we can use to very accurately measure masses of these really strange, really beautiful giants. And this is what roughly this black hole looks like if simulated in Space Engine. And by the way, just a small side note, just in case you might get confused, the actual disk that was being measured is not the same as the accretion disk that you see here or that we saw with the M87 black hole. The accretion disks, because they're so much smaller in size than the cold gas disk, are not really that easy to use to calculate masses of black holes. So even though here this is kind of what you see, the actual cold disk would be on much grander scales. The size here is only roughly around maybe 1 light year, whereas the actual cold disk would be anywhere from a few hundred to a few thousand light years across. And this of course means that maybe one day we'll be able to combine these two techniques and create a way for us to measure a lot of things out there in the universe very precisely. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new discovery related to black holes, or I guess more technically, a mystery related to black holes, possibly a new type of a black hole. So today we know quite a lot about black holes, even though we've only seen just a few. Normally our understanding of black holes comes from mathematics and from just the observation around us, and specifically from the objects like the one you see right here. These objects normally are really difficult to see because, I mean, black hole technically is black, with the exception of black holes producing Hawking radiation, of course. And the only way we can technically see a black hole is when it interacts with something. This right here is what's known as an X-ray binary. These objects are black holes that have a partner, and the partner is hiding somewhere in the back there, although it will be very difficult for this partner to hide because it's essentially an extremely large star. This right here is the object known as Cygnus X1, a black hole and a very large star relatively close to one another. And because there is an interaction between them and the black hole is able to consume a lot of material and produce a lot of energy, this is essentially how we're able to see it. And so, just recently, we've discovered another similar black hole in our own galaxy. This X-ray transient known as Swift J1357.2, and so on. And so this particular object is also an X-ray binary and has relatively similar effects overall, but it does have something really unusual about it, and today I'm going to talk about it. And by the way, if you'd like to check out the paper, it's also in the description below. But also, just for fun, let's try to make our own X-ray binary or X-ray transient with the sun right here and a 10 masses of the sun black hole in the middle. Now, it's super tiny, as you can see, it's only a few kilometers across, but this black hole is essentially a very massive body that's about to turn our sun into its own meal. And I don't know how long it will take for the sun to fall apart, but it's not going to take a long time. But as soon as we start running the simulation, you'll notice that the sun is going to start losing matter due to the tidal effects from the black hole. And all of this matter will eventually make its way toward the black hole and then get consumed, produce the accretion disk, and at the same time release a lot of energy that we'll be able to detect from a very far away distance. There you can see the sun losing the actual mass already, and some of this mass will eventually make it to the black hole. And so these X-ray binaries are well studied. We've known about them for a very long time, and we understand them quite well, except for the one we just discovered. We'll come back to our system we created here in a few minutes, but let's talk about the discovery. This beautiful picture that was created by John Pace demonstrates sort of what's happening here. So just like with the other X-ray binaries, we have the black hole in the middle, we have a sort of smaller star orbiting around it, potentially even inside the accretion disk of the black hole, and this star is a donor. It's donating its mass to the black hole, which then creates the beautiful accretion disk and the energy we're seeing being emitted toward us. But back in 2017, the scientists looking at this binary discovered that it suddenly became extremely bright. It had an eruption. It's very likely this happened because too much material was accumulated in the accretion disk and it literally just exploded. It initiated a nuclear reaction and created what's known as a nova. While at the same time, when looking at this black hole, they discovered that for some reason, every 2 to 10 minutes, it also dims periodically. It becomes less bright and then goes back to its original brightness with no explanation. So in other words, there was something happening in the accretion disk of this black hole that was causing these unusual effects. And so by using this beautiful South African large telescope, also known as SOLT, they were able to identify exactly what's happening. They realized that during those dimming effects, something unusual was happening inside the black hole, or very close to the black hole. It was, for some unknown reason, releasing a tremendous amount of gas that was being shot in every direction, including, of course, toward us. So right there, during the dimming effect, they were able to see huge clouds, or technically streams of helium gas, being propelled at us at the speed of about 600 kilometers per second. Super fast. So basically, it was sort of blowing out this huge amount of wind that was being emitted in every single direction. And this is something we've never really observed around a black hole before. And the scientists behind this paper believe that the only reason we were even able to see this dust and this wind coming at us is because, well, first of all, the black hole itself is positioned in this way to us. We're literally looking at the side of its accretion disk. But there was a part of an accretion disk where things are just not really flat. In other words, it's almost like a warp or a break in the accretion disk that is visible right here in this image that allowed us to see what's happening close to the black hole. And this is something that happens every 2 to 10 minutes. So as the accretion disk orbits around the black hole, every 2 to 10 minutes, we get to see the inside. And what we're seeing is this really hot gas, about 30,000 degrees Celsius, being emitted at us at 600 kilometers per second. And so if it wasn't for this unusual warp, we wouldn't really even see it. We wouldn't even know that this existed. But we're not really sure if this is a common occurrence. We don't actually know right now if any other black holes out there have this unusual phenomenon. But as of today, this is the first such black hole discovered, and so the scientists behind this paper proposed an unofficial name. Basically, this is the first accretion disk corona discovered. Or in other words, it's the first ever black hole that seems to have these unusual, really fast gas emissions. Now, this is a pretty good representation of what we're looking at, except that this is of course a picture of our own sun, with the sun itself being blocked out by a dark object. And so this is technically a very unusual and very peculiar black hole, and we can't really explain why it has these unusual effects. I'm pretty certain that we're going to have a lot of follow-ups and a lot of additional investigations trying to discover what's causing this. But it might be just a new effect that we've never seen before, or it might be some sort of an unexplained phenomenon that we need to definitely investigate. Now, going back to our own black hole that we've created, let's see what happens to our own sun as it orbits around this black hole that's very similar to what we've observed in the system I just described. So here we have a relatively small star, and as you can see, the accretion disk is being formed by the star falling apart. And some of these parts will start slowly approaching the black hole and then falling into it. So this is kind of how these accretion disks are formed, except that in this case, we're looking at it from this direction. And the accretion disk is so bright and the star is so small that we don't even see the star itself. Well, we barely see the star. But unlike in this paper I just described, this black hole doesn't really have any corona. There's nothing coming out of it, and there's nothing being emitted out of it either. And so this is why I think this paper definitely discovered something unusual that we need to investigate a little bit more. So let's just run this a little bit longer and see what happens to our sun and of course to the black hole itself. Hello wonderful person, this is Anton, and can you guess what you're looking at? Well, you can probably tell from the title. This is the supermassive black hole in the middle of our galaxy. And those little fireflies you see in the middle that are a little bit easier to see if I come closer are stars orbiting in the central region. Now, this is a little bit accelerated though, so obviously they don't move this fast. But today we're going to be talking about the chance for these stars to have actual planets and possibly even worlds similar to Earth. Not so long ago, in early 2000s, the scientists finally identified the region in the night skies where we now are absolutely certain our supermassive black hole is located. This region is known as Sagittarius A star, and we're actually zooming in there right now. One of the reasons we know for a fact that there's a supermassive black hole is something you'll see in a few seconds. This is an actual video taken by the European Space Observatory. So right there in the center, you'll notice that some peculiar motion is quite apparent. And this is going to be those stars that I just showed you. They're going to be orbiting around something in the middle. Now, the fastest object that you see orbiting is known as S2. We've talked about this object many times on the channel because it's one of the more well-known stars in this particular region. And this star comes really close to the black hole and moves at something like 2500 kilometers per second when it's that close, about every 16 years. But as you can imagine, there are a lot more stars here, and many of them are interesting in their own right. There are roughly around 40 stars specifically that we're interested in, and although some of them do come really close to the black hole, some of them stay relatively far and are not really as affected by it. And one of the stars in this region, known as S85, has the longest orbital period. It orbits around the black hole every 4,000 years or so, actually about 3,800. Now, all of these stars are interesting to us, but specifically because we would like to know if there are also planets around them, and either the planets that were captured from the outside, or more interestingly, planets that came with these stars, because we're pretty sure that almost all of these, if not all of these stars, were from other regions. They basically fell into this region because of the interaction with something else, like for example with a partner that they might had, and maybe even another black hole, and all of these stars ended up being attracted to the black hole one way or another. But we know that about 32 of them are relatively young, about 8 are pretty old, possibly even 3 billion years old, and so many of them might possess planets, and many of them might even possess terrestrial planets. So this is something we would like to find out one day, which is why discovering this study from the Italian scientists was pretty exciting for me. Now, it's still not entirely finished, they're still processing their data, but they already have a lot of initial results that show us what's most likely going to happen if these stars do have planets. So basically what these scientists did is use a relatively simple simulation, very complicated compared to what I'm using here, which is Universe Sandbox. Their simulation is known as AGRF code, and they essentially simulated the orbital parameters of various stars orbiting a black hole. So basically, let me help you visualize this. There is Sagittarius A star, here is our sun for comparison, and we're going to place a planet around our sun. Or actually, let's just place all of the solar system planets, including of course our beautiful planet Earth that's right here, and we're going to see if any of them stay in orbit around the sun. Now this sun orbits a little bit close to the Sagittarius A star compared to some of the other stars, but this will give you an idea of how basically nothing will stay in orbit around our sun. Everything instantly gets dislodged by the tidal forces of Sagittarius A star and becomes its own object. And so here, Sun is completely alone. None of the planets stuck to it. Now that's possibly because the Sun that we have here is a little bit too close. If we were to place it maybe a little bit farther away, like somewhere right here, it might have a better chance to maintain some of the planets. As you can see, the planets like Uranus and Neptune didn't really stay with us, but we still have Saturn and Jupiter, it seems, at least for the time being. If we run this a little bit longer, we might see what happens with these orbits after, but a lot of these planets do get tidally disrupted, and eventually you can see that even Saturn is losing its orbit slowly. So this is the effect of having tidal effects from a very massive, extremely gravitationally potent object like Sagittarius A star. And for this reason, the simulation was actually really long. It took them a pretty long time to run through this, because they were simulating 40 different stars for roughly around 4,000 years of very realistic orbits. And they decided to do just this. They decided to place 8 planets around these stars. Actually, I believe only the older stars got the 8 planets. Okay, we lost Jupiter, we lost Saturn. And so only the more ancient stars, like S85, that's probably a few billion years old, were given all 8 planets, because we think it takes a while for star systems to develop an actual planetary system. The younger stars, like the famous S2 that you see right here, were only given, well, essentially gas giants. Only objects like Jupiter, Uranus, and Saturn. And so once they ran the simulation and looked at the results, they were actually quite surprised to find out that pretty much all of the stars maintained at least one planet, specifically Mercury, because it's the closest. And just like in my simulation right here, you'll see that the terrestrial planets are actually not very difficult to keep, to maintain. So even the Sun here will probably keep these planets for quite a while. Now the results you can see in the paper and description below, but it sort of looks like this. You can see that every object had their Mercury after 4,000 years. A lot of objects, about 72.5%, had Venus and Earth, and even Uranus, which is a pretty far away object, was still maintained around certain stars. Now, no Neptunes, but that's okay because these are pretty far, but the chance for having at least 1 or 2 terrestrial planets around the stars in the central region is now actually pretty high. So it seems that there is quite a lot of chance that if these stars came with planets and some of them were terrestrial, that some of these planets are still there and they're orbiting along with their star around the supermassive black hole. Which of course raises the next question. So what exactly would happen to these planets? What's going to be the effect of all of this radiation and all of these extremely powerful astrophysical jets coming from the black hole on the planets themselves, on the atmosphere, on any kind of materials on the surface? All of this would really need to be investigated and possibly simulated, because it's very likely we're not going to be able to see this anytime soon. It would be extremely difficult for us to actually zoom into these stars. We just don't have a telescope that's big enough. We would have to build a telescope that's size of our solar system. But we do have really powerful computer simulations, including some really special supercomputers that could definitely simulate the effects of a typical supermassive black hole on the surface of a nearby planet. And this is something that I hope someone does in one of the future studies, because it would be super interesting to find out what happens to planets. And so anyway, that's really all I wanted to mention in this video. Once we discover more about this study and once we have more results, I'll make sure to do a follow-up video explaining, especially if there's something interesting that they discover. But for now, that's it. So now we can kind of assume that there are planets orbiting around stars very close to the supermassive black hole, simply because it's very likely that some of those stars had these planets, and simply because it's kind of difficult for them to lose planets like Mercury. And maybe one day we'll even get to see a typical planet passing in front of the star in this region, and then discover an exoplanet extremely close to the supermassive black hole. Hello wonderful person, this is Anton, and today we're going to be talking about black holes and galaxies. And more specifically about a recent discovery that one of the relatively large galaxies out there seems to have a tiny black hole in the middle. And that goes against our ideas of black holes, supermassive black holes, and galaxies. So this right here is our own galaxy, and this is the Milky Way, and in the middle of the Milky Way we have our central supermassive black hole known as Sagittarius A star. It's approximately 4.3 million masses of the Sun, and when it comes to comparing this to some of the other supermassive black holes, it's actually sort of on the smaller end. But what we know about it is that, well, first of all, it's not actually that active. It's not really absorbing that much material right now, and it's also not really producing that much radiation, but it is still absorbing some mass. And sometimes, once in a while, we'll get these astrophysical jets that you see right here. But some other black holes, like for example the super famous M87, are roughly around 2,000 times more massive. And that's why we were able to take such a good photo of this black hole, because it's larger, it's more massive, and everything here happens a lot slower, so it's easier to take a picture. Yet there are galaxies out there like this one right here, NGC 4395, that's roughly around 14 million light years away from the Milky Way, that seems to hide a bit of a mystery on the inside, and it's something that scientists can't really explain or understand. This galaxy is not small, it's about 50,000 light years across, still smaller than the Milky Way, maybe about 3 to possibly even 4 times smaller than the Milky Way, but it is not a galaxy that you would call tiny. It's considered to be a dwarf galaxy, but compared to, for example, our partner Large Magellanic Cloud that you'll see right there, and actually let's zoom into it just to see what it looks like, it's roughly around double the size. So it's not tiny. But the mystery with that particular unusual galaxy is that we always knew that something in the middle makes it unusual. We always knew that despite being an active galaxy, what's known as a Seiffert galaxy, where you can actually detect a lot of activity coming from the middle of the galaxy where the black hole is located, for this particular galaxy, it just seemed like the black hole was a lot smaller than we anticipated. The initial calculations suggested that it was maybe only a few 100,000 masses of the Sun, which would make it roughly around 10 times or even more than 10 times smaller than Sagittarius A star, but even that didn't really make sense. And let's actually jump to that galaxy in Space Engine so we can see what it looks like. So this is what it looks like, and as you can see in the center there, it is a lot brighter than other areas. And that's because its center is considered to be active. It's an active galactic nuclei. And that's because the black hole is absorbing stuff, it's creating all this energy, and technically it should be growing pretty fast, but it's not. And the recent paper that you can find in the description below discovered that the black hole in the center of this beautiful galaxy is roughly only about 10,000 masses of the Sun, making it the smallest ever central galactic black hole discovered, and technically also unofficially qualifying this as the first ever intermediary black hole that was confirmed through various observational means. At the same time, it's basically an anomaly. It doesn't make sense. Now, what we understand about black holes is that they do seem to interact with nearby space, nearby stars, and specifically with the central bulge and the central region that we're currently entering. And this interaction then propagates to the rest of the galaxy. But for this unusual galaxy, the interaction is a lot more difficult to explain. Now, if this black hole is the only black hole that's available in the region, which it seems that it is, why is it so small? Why did it not get bigger? How did it not become a giant, considering that it's actually in the middle of a relatively large galaxy? Even though it's a dwarf galaxy, it's still pretty massive. And most importantly, what actually makes black holes stay so small? And what makes black holes like Sagittarius A star or M87 get so big? So this discovery created a lot of questions that need to be answered. But before I continue, let's actually also talk about how they were able to determine the mass of this black hole. The technique itself is not very new. It's something that we've known about for a while. And the way that it's done is by measuring the interaction between the radiation coming from the accretion disk of the black hole and the gas clouds that are usually located much farther away, that sort of orbit around the black hole and are usually the leftovers of stuff, or various gas particles and dust that kind of settled in the orbit farther away from the black hole. And we've discovered their relationship. The more massive the black hole, the farther away this gas kind of orbits. So for example, for Sagittarius A star black hole, which is this one right here, this would be at a certain distance, but for M87, which is more massive, it would be much, much farther away. And so the scientists behind this paper, knowing and understanding how this dust cloud works, were able to calculate that for the radiation from the accretion disk to hit the dust cloud, it took roughly around 82 to 83 minutes. And the way that they found this is by basically knowing that the radiation escapes and then hits the dust cloud that normally will contain quite a lot of hydrogen. And when the radiation from the accretion disk hits this cloud, it actually makes it emit very, very specific and very easy to recognize types of light. And so they were able to determine that it takes it about roughly 82 minutes to get from the accretion disk to the cloud. And using this and also understanding the speed of the actual cloud, they were then able to estimate the mass at roughly around 10,000 masses of the Sun. You can find out more detail and more math, of course, in the paper in the description below. And well, this discovery is very unusual. That's probably not the best word to describe it. It's very peculiar. It's hard to explain. It's hard to understand. And most importantly, it creates this new opportunity for study for us, where we now know that, well, some galaxies have really tiny black holes in the middle, and they still are active, they still produce a lot of energy, but they're not as massive as some other black holes. And that is, we really can't explain it. We can't really understand how this could have happened. And so, unfortunately, on this note, that's really all we've discovered so far. Now, I'm pretty sure there's going to be a lot of follow-up studies and a lot of follow-up observations to try to find out what's really happening here, because it is such an unusual and such a strange discovery. Now, I actually also wanted to go in the middle of the procedurally generated galaxy in Space Engine and find out what Space Engine thinks about all of this. Space Engine is based on very accurate mathematical representations, and so here we can try to discover what the black hole is according to Space Engine. So let's go and find it right now. And it seems to be somewhere in the middle of this globular cluster because that's where I'm being pointed at. So let's go in the middle and look for that central black hole of NGC 4395. And my guess is that it's going to be larger than 10,000 masses of the sun. It's probably going to be massive, more massive, possibly even 1 million masses of the sun. And looks like we've found it. So there it is with all of its planetary and star companions. And that object in the middle is that black hole. But let's discover how massive it is. Okay, here we go. And there's that black hole. Let's come a little bit closer. And I think that's close enough. And according to the space engine, the mass of this black hole should be, technically, roughly around 990,000 masses of the sun. And that's kind of what the logic suggests, right? But in reality, it is something like 99 times less massive. Hello wonderful person, this is Anton, and you're looking at the first ever simulated image of a black hole created by an absolutely incredible scientist by the name of Jean-Pierre Luminet, who also wrote the article right here about the effects of super fastly spinning black holes. I've talked about this in one of the previous videos, but you can find this article that's totally worth reading in the description below. Anyway, today we're actually talking about the most, or I guess in my opinion, the most unusual black hole out there in our own galaxy that was discovered back in 1992, but has actually since not really been that well studied because it's sort of far away. Its distance from Earth is approximately 30,000 light years, and that's about pretty much the center of our galaxy from where we are. If you know anything about black holes, you know that we might have about 100 million of them in our galaxy, but because they're not really emitting that much radiation, it's very difficult to see them. There might be a black hole within about 30 light years away from Earth, but we're gonna have trouble finding it. This could be one of those black holes. This is just a simulated one in Space Engine, but we're not going to be able to find it without any advances in technology. However, the black hole I'm talking about today, that's located in this direction from planet Earth, is one of those black holes that has another partner. It has a very large star orbiting with it, and this is how we were able to see it because of the effects it had on its partner. Let's jump into it and let's take a look at what's happening here. So first of all, you'll notice that the partner is relatively close to the black hole that is right there, and because of this, it's actually losing a lot of material. It's losing a lot of mass. A lot of the star material is being kind of sucked into the black hole, and that produces really, really powerful astrophysical jets. And although they might not appear as powerful here, they are very, very, very strong. And all of this is because it's literally just eating away at this star next to it. And because of these jets, this black hole is now also known as a microquasar. It's essentially pointing its jets at us, just like this, and we can see the radiation coming from this black hole, and this is how we were able to detect it at such a far away distance. But this is not actually the weirdest part about this black hole at all. Today we know that this is one of the fastest spinning black holes out there. Its actual spin is so fast that if it's spun even like a 0.1% faster, it would not possibly exist. It would probably just disappear completely. It would fall apart. We believe that this black hole spins at something like 1,150 times per second. Now this is with the size of about, it says here about 80 kilometers in diameter, so that's about maybe 40 kilometers in radius. And at the same time, this black hole is also very massive. It's one of the most massive solar mass black holes we've discovered. Its mass is about 18 masses of the sun. But if you were to look at the edge of this black hole, this right here would spin 1,150 times every single second. That's how ridiculously fast it spins. This is essentially almost the limit. And because of this ridiculously high spin, this black hole also produces really strong dilation effects, specifically things like time dilation. If you've watched Interstellar, and also if you read this article that I posted about the warp science of Interstellar, you'll discover that spinning black holes produce a lot of unusual effects. Some of those effects could one day be used by humans, or I guess wherever aliens discover a way to approach black holes, to produce pretty much unlimited energy. I've discussed this in a video you can see above my head. That's a video on halo drives. The quick summary, if you don't want to watch it, is that, and by the way, you probably should watch it because it's another really awesome study, but the quick summary is that if you were to fire a laser or really any power source at the region of a black hole right here, known as the ergosphere, it would come back to you with more energy than you gave it. And you can use this to accelerate. You can also use this to produce ridiculous amounts of energy out of nothing by taking away the energy from the black hole itself. Now, this only applies to spinning black holes though, and every time you steal a little bit of energy from this black hole, it will actually spin a little bit less fast. Now, because of its mass and because we're talking about a mass of about 18 masses of the sun, it will take a huge amount of energy to slow this black hole down, so there's a lot of energy to be taken here. And also because of its spin, if you were to actually be right at the edge of this black hole, so I guess kind of right here, you would also experience quite a lot of time dilation. This is when the time for you starts moving differently, and if you were to leave this region, you would actually find yourself in the future. Once again, kind of like what happens on the Miller planet in Interstellar. Maybe not to that extreme though, but quite noticeable nonetheless. However, because this is a solar mass black hole, if you were to come this close to it, the tidal effects here would actually rip you, and not just you, but even your atoms, into pieces. Today, most scientists refer to this effect as spaghettification, and here's a somewhat interesting picture trying to depict it. Your body will start experiencing tidal effects, or effects of gravity, different at different places, and at some point even your atoms will feel different effects, and this will stretch your body and your atoms into this long spaghetti-like shape that will eventually get sucked into the black hole as you're experiencing this very miserable death. Now, we don't really know if we'll ever reach the point when we'll get to actually see anyone die from this. Probably not, but nevertheless though, just the fact that we know that this is something that happens is quite remarkable. Now, I personally definitely hope that one day we'll be able to use similar black holes for extraction of energy and of course space travel, but it's probably not going to happen in my lifetime, simply because the closest black hole to us would be at least maybe 30, 40, 50 light years away. And getting there would take, I don't know, at least a century starting today. I don't know if I'll live that long, but you never know, right? Anyway, so that's the black hole. That is probably the weirdest and the fastest spinning and also the most massive solar black hole that we've discovered so far. This is definitely one of those black holes that will most likely teach us about these unusual phenomena a lot more. But most importantly, we're hoping to discover a similar black hole very close to us. That black hole would actually teach us even more and possibly would allow us to travel across the galaxy way faster. If you'd like to explore this particular star system by yourself, this is available in Space Engine, which is a free tool that I used here, and the name for this is GRS 1915 plus 105A. And as you can see, this is the binary that we have here. And by the way, these are binaries that we refer to as X-ray binaries because this is how we discovered that this was a black hole. It was producing so much X-ray radiation that it was impossible to be explained in any other way. The only way that these X-rays could be created is if the star was losing all of this mass, it was falling into the black hole, and as it was falling into the black hole, it was producing tremendously powerful astrophysical jets that we then detected in X-ray radiation. So that's basically it for the fastest spinning black hole in the galaxy and potentially one of the fastest spinning in the universe. Now, it still is not as fast as the black hole in Interstellar, but that black hole was spinning a little bit beyond the limits of real black holes. In other words, it shouldn't have been spinning that fast. Hello wonderful person, this is Anton, and in this video we're going to be talking about a black hole calculator. and more specifically a calculator that allows us to find out how much energy and how much mass is released or absorbed by a black hole when it collides with something else, or actually when something collides with a black hole. Now, this black hole here is procedurally generated in Space Engine, and it's actually a really cool star system. Here we have a very unusual brown dwarf, or an L-type star, that seems to also possess a few planets. I discovered this completely by accident, but thought it was actually a pretty good opportunity for me to talk about black hole collisions. So this here is actually not a star, it's more of a planetary object. It's a brown dwarf. Its mass, according to the simulation, is about 35 masses of Jupiter, and the reason why it does look like a star is simply because it creates a lot of heat from the inside, but it doesn't have a nuclear reaction just yet. And this object also has its own planets, although technically I guess you would call these moons, because if it's a brown dwarf, these have to be moons. So these objects, these moons, orbit around a black hole. Although I guess it's a little bit off topic, but if you look really closely, you discover that even these moons have their own moons. So they're technically moons of moons, or moons. And here you can kind of see both of them moving across the night skies. But anyway, what we really want to talk about is, what if all of these objects, and specifically I guess the brown dwarf itself, collided with the black hole that's in this system? Because right now, if you look at the system, the objects in the system all orbit around the central black hole that's right there in the middle, with the black hole itself possessing several planets as well, suggesting that it's a really complex system. And we believe that these systems do exist, we just haven't really seen any just yet, mostly because it would be very difficult to find these black holes, unless of course something collides with them. And to help us answer all of these questions, a particle physicist by the name of Alvaro Diaz created a beautiful and a relatively simple calculator that you can find in the description below, that allows us to quite easily find out the parameters of a typical black hole if something collided with it, and also the amount of energy released during this collision. So for example, let's just say that we have a black hole that has a mass of 5 suns, and here a typical event horizon for this black hole would be about 14.77 kilometers. And if we were to try to imagine this black hole in Universe Sandbox, this is sort of what it would look like. It's a pretty small, tiny spot right there in the middle, with the size of, I guess, a relatively large city on the planet Earth. So let's just say that something falls into this black hole. Let's start with a typical star. So here we have a star that's about 3 masses of the sun falling into this black hole. And you'll notice that at the end of the collision, the mass of the black hole is 7.91 masses of the sun. Its event horizon has increased to about 23.4 kilometers. And this number shows you the total growth of the black hole in terms of size, so it grew by about 58%. But why exactly is it not 8 masses of the sun? I mean, 3 plus 5 should be 8, right? Well, during the collision, we also released a lot of energy, mostly because of the relativistic effects caused by the acceleration of matter here as it falls into the black hole. So right at this moment when it starts falling into the actual black hole, a lot of the matter will be moving so fast and with so much kinetic energy that it will essentially transfer all of this mass into energy, and it will generate a really large explosion, which unfortunately didn't really happen here because our black hole just kind of ate everything. In reality though, it would look something like this. There would be a very, very powerful, very large explosion, essentially equivalent to a tremendously powerful supernova. And in this case, from, I guess, 3 masses of the sun, the amount of energy released is equivalent to 322 Bethe or Fo, which is a unit used for really large amounts of energy. And a typical large supernova, type 2 supernova, will normally produce about 1 Fo of energy, normally maybe a little bit more, 1.5 or so. So this collision generated 321 times more energy. And that's by using a relatively small size in terms of mass. It's a little bit more massive than our own sun, but way less massive than some of the other stars out there. Okay, so let's try this with something else. Oh, and by the way, so the 0.09 masses of the sun became this. This is the energy released that used to be mass. So now let's try this with the brown dwarf that we have in this system. First of all, this black hole has a mass of exactly 5 masses of the sun as well. I think that's completely by accident. and it's going to be colliding with an object that is equivalent to 35 Jupiters, which according to my calculator is equivalent to 11,130 Earths. And here, obviously, the mass of the final black hole is not really dramatically larger. It only increased by about 0.64%, but look at the amount of energy this releases. 3.5 more than a typical supernova. So even a brown dwarf like the one you see right here, that's technically just a planet, if it were to collide with a black hole, it would release more energy than a typical supernova. And it would be visible from pretty much everywhere in the galaxy, at least if it happened in our own galaxy. So since we haven't really seen that many events similar to this, we know that these events are not very frequent. We haven't really seen any unusual supernova happening for no reason in the last few decades, or basically since the advances in telescope technology. And because of this, we believe that black holes basically absorbing planets or absorbing stars is not a very frequent phenomenon. But obviously even a smaller object like a moon would produce a tremendous amount of energy, which is why even though very small particles are falling into the supermassive black hole in the middle of our own galaxy, Sagittarius A star, even these tiny particles will produce enough effect for us to see from really far away. This is at a distance of over 25,000 light years away from us, and we can normally see them pretty easily. And a few months ago I reported that there were these unusual flashes in the middle of our galaxy that suggested that something was happening there and something was being swallowed. You can actually check out this video in the description below. And this video with, I guess, this guy right here, this is Anton in the past, did not really explain what was happening, but we know that something was swallowed by the black hole. And that something did not have to be big either. It could have been just particles. Because the amount of energy that is being produced by a typical black hole when it swallows something is absolutely mind-blowing. Now, before I finish this video, I wanted to do one more calculation. I wanted to actually find out what would need to be sort of swallowed by a central black hole in the middle of our own galaxy for it to become really dangerous for us here on Earth. In other words, let's just say our black hole swallows something and it generates such a tremendously powerful flash that suddenly this flash becomes deadly to humans, to basically life here on Earth. Now, the only thing we can kind of speculate here is, of course, what exactly would be dangerous. And based on the calculations, if, for example, a supernova happened at a distance of about 30 light years away from our planet, it would be pretty dangerous. Most scientists believe that the amount of radiation produced here would be quite detrimental to the atmosphere of our planet and might even cause some kind of an extinction event. So let's just say that what we have to produce is the energy equivalent of a supernova at a distance of about 30 light years. Well, if you were to try to estimate how much energy has to be released at a distance of 26,000 light years away from us, there's a very easy formula we can use for brightness versus distance that allows us to calculate how big of an object it would have to be. So here, if we travel every single part of a distance, the relationship here is described as luminosity over distance squared. So in other words, for a distance of about 26,000 light years, which is about 1,000 times more than the distance to a potentially dangerous supernova, here what we'll get is about 1,000,000. So in other words, if something equivalent to 1,000,000 supernova happened at a distance of 26,000 light years away from us, it would be potentially dangerous to planet Earth. And using this calculator here, we can totally figure it out. So first of all, the black hole mass for Sagittarius A star is about 4.3 million masses of the Sun. This creates the event horizon of about 12.7 million kilometers, so it's a really large event horizon. And now what we have to do is figure out how much mass we need to actually throw into this black hole if we want to create something equivalent to 1,000,000 supernova. If this object is about 1,000 suns in mass, it will already generate 107,000 Fo, which is about 1/10 to where we need to be. So here, an object that's about 10,000 suns will generate nearly enough energy to potentially cause some kind of an extinction event. And although this is a very simple calculator and it implies that this object has to be a single piece, we could still use these results to estimate the total mass of matter that would have to fall into the supermassive black hole to create enough energy to cause potential concern for Earthlings, which by the way would also turn our beautiful black hole that's relatively inactive right now into what would basically be a quasar, an active galactic nuclei galaxy that has tremendous power generated in the center that prevents not only life from forming on planets in this galaxy, but it actually also prevents the formation of stars. Now, 10,000 masses of the sun might not be enough to do that, but it's definitely enough to maybe destroy life on Earth, or at least cause a massive extinction event. Hello wonderful person, this is Anton, and in this video we're going to be discussing a new, unusual study and a new mystery that might resolve a lot of other mysteries. Today we'll talk about what are known as geodes, and something that might resolve the problem with dark energy, while at the same time explaining a few anomalies we've observed when black holes collided. So in the last few years, we were able to discover quite a lot of really cool things. For one, we actually got to take a picture of a black hole, of a galaxy known as M87, and this black hole even has a name now, it's known as Poehi. At the same time, we've even observed things like stars being eaten or being absorbed by black holes, and we've seen many different black hole and neutron star collisions as well. All of this is something we've theoretically expected to happen, but finally we got to observe them using various new techniques and various new observatories out there. But at the same time, there are still a lot of unanswered questions. One of these unanswered questions is of course related to the so-called dark energy. The idea behind which I can explain to you very easily by basically taking a look at this simulation here. Today we understand that our universe is expanding, but for some reason it's also accelerating its expansion, and it's something that we are having trouble explaining. As an explanation, we've proposed this idea of dark energy, this unusual, I guess you can call it substance, that exists in the universe that's causing this acceleration, that's kind of pushing things apart more and more and more. And it's something that we've observed, but we just can't really explain it. At the same time, when it comes to black hole collisions, we've also seen quite a lot of them. But even the first collision we've ever seen was a little bit unusual. As a matter of fact, we've predicted these collisions to first of all be a little bit more rare, but at the same time we've expected the actual black holes to be much smaller, much less massive. The collisions we've observed were basically between black holes that were about 30 masses of the sun, and that's way more than we predicted, and it's something we couldn't really understand or explain. In other words, just to help you visualize this, even though we predicted it to be sort of like this is a typical black hole we thought we would see, we instead saw something like this. Much larger, much more massive black holes colliding, forming an even bigger black hole. And this is something that we kind of have taken for granted now, because we've observed a lot of these relatively large black holes. This is about 30 masses of the sun, but still, it's not really something we can explain theoretically. And so to try to explain all of this, the two scientists who published this paper decided to describe this in slightly different terms. They decided to combine ideas from the Soviet physicist who, back in 1966, when he was much younger than you see on the picture here, proposed the idea that, well, maybe, just maybe, certain black holes can actually become dark energy chunks. And today we refer to these objects as geodes, which stands for Generic Object of Dark Energy. And the idea here, well, is kind of difficult to explain mathematically. As a matter of fact, when I was reading this paper, there was so much math in it that I had to take a very long break and then come back and try to finish it. But in essence, imagine it's an object that instead of being a black hole is actually made out of this dark energy. And even though it sort of appears as a black hole from the outside, inside of it is a different story. Inside it's basically all just dark energy matter, or I guess dark energy substance? Dark energy. And to try to explain all of this, the scientists in this paper proposed that everything in the universe is essentially kind of connected. Basically, the black holes and the dark energy, they all influence each other, and when these geodes are created, they sort of start influencing the rest of the universe and pushing everything apart. And so in a sense, they are suggesting that there's an interconnection between these really small compact objects like black holes and more specifically geodes and the rest of the cosmos, the rest of the universe. And so as a consequence here, what this suggests is that the growth of the universe itself actually kind of dictates what happens to the stars when they die. if they become black holes or if they become geodes. And according to the scientists behind this paper, even if just 1 out of 100 black holes is a geode, which might look something like this, and if just one of these black holes is a geode, it would be enough to explain the effects of dark energy that we're observing across the universe. And honestly, this is actually a pretty interesting discovery, or at least a pretty interesting theoretical mathematical analysis. So here, a single black hole as a geode is enough to explain what we're observing, and enough to explain the anomalies we've seen in LIGO black hole mass detection. In other words, if two of these black holes collide and they're not really black holes but they're geodes, they would produce the masses that were observed. Because according to them, if you were to look at these geodes from a distance, from a faraway distance where these two geodes collided, they would actually appear more massive than they really are. And so this is kind of how they explain both the anomalies in the LIGO detection and the so-called dark energy that they believe might be all connected to these unusual objects. These geodes would also kind of grow in size with the universe until basically the collision occurs. And so in a sense, these objects are literally like a connection to the rest of the universe. As the universe grows and expands even more, so do these geodes and of course their influence on the rest of the universe. But of course this is all very theoretical right now, it's basically all mathematical even. There is unfortunately no actual evidence that this might be true. And even if these geodes do exist, we have no idea what's inside of them, we don't even know how to possibly find them, because they would kind of appear like a typical black hole. As a matter of fact, the scientists behind this paper even suggested that maybe the Poway black hole in the middle of M87 is also a geode. It would appear a lot more massive from this distance, but in reality it could be basically made of dark energy. But unfortunately there's really no proof. I'm sure it will probably take years before more scientists will join and try to analyze their study and also try to come up with maybe some observational proofs. For now, we don't really know, but of course it's a good explanation to both dark energy and the unusual observations that we've seen. If, however, the scientists behind this paper are correct in their assumption, it really means that maybe, just one single black hole being a geode is enough to explain the effects we're seeing with dark energy. And it also means that this Soviet physicist was way ahead of his time in trying to explain something that we didn't even know existed back then, because we've only realized dark energy might be a thing in 1998, but he came up with this idea back in 1966. But anyway, until we learn more or until we get more studies in regards to this idea, that's really it. If you'd like to try and read this and possibly test your math skills in trying to understand how all of this works, the link for this paper is in the description below. But for now, that's really it. Thank you for watching. Hopefully now you know a little bit more about the universe and our understanding of it, or I guess in this case, our not understanding of it, because we're still not really sure what dark energy is. Hello wonderful person, this is Anton, and this here is the system known as V404 Cygni. This is one of the most well-studied and one of the most well-known systems because it contains a black hole that's currently the closest black hole we've discovered, at a distance of just over 7,800 light years away from us. Basically, really far. And although the large object in the middle is not a black hole, this tiny spot right here is. So today we're going to discuss what we have recently discovered about this unusual but very powerful black hole, and we'll also talk a little bit more about what this might mean to black hole research in general. So only a few days ago from when I'm making this video, this research showed up in Nature magazine. It was about the most famous black hole V404 Cygni, and it talked about how it has a very unusual, very hard to explain orientation of its jet compared to the actual spin of the black hole, and also compared to the orientation of the accretion disk right here. In other words, something strange was happening here. Now, first of all, what exactly do we know about this black hole and why is it so famous? Well, this black hole is, like I said, the most well studied so far, and we've officially learned most of the things about black holes by studying this particular star system. And that's because, as you can see, it has a very, very large partner. And it's essentially eating away a lot of the mass and a lot of the material from its partner, absorbing it and then releasing it as tremendously powerful astrophysical jets. And these eruptions, as you can call them, happened several times, and most recently in 2015 we were able to observe them with a lot of detail. But they actually happened a few decades prior, back in 1938 and also back in 1956. And it's very likely that it's going to happen again, possibly maybe 20 or 30 years later. And this is actually based on the fact that the first time we observed this black hole was back in 1989, when it had a somewhat similar outburst as well. So this black hole, as you can see, is it's very small first of all, but it's very massive, and it has enough mass to absorb and then re-emit a lot of material, but it does so in a very strange fashion, and this is actually a very good representation of what it's doing. So let's go back a little bit before I show you more, and first look at what was detected back in 2015. This is literally all we saw, and as you can see, these tiny pixels don't really show you much. Unless, of course, you're a seasoned astrophysicist and you know exactly what's happening here. And what was unusual about these particular missions is that they were somewhat repetitive, but also the actual luminosity of these emissions was not constant, as if this object was spinning on the side, as you can see right here. Essentially as if it was some kind of a pulsar. Or I guess in some sense you could call it a lighthouse, if you were to use more earthly terms. Although the actual observation itself may have not really been that exciting, what was unusual about it is that it was just not constant as we would expect from a typical astrophysical jet from a black hole. And this was only visible if you were to look at this with very short exposure. In other words, if you were to only look at this for a few seconds. If you were to take a longer exposure, you would actually see a much blurrier image, sort of similar to how the image of M87 appeared. So in other words, you had to use very short exposure to see these unusual flashes. And the major explanation for this was that the black hole itself was orbiting in this way. It was actually kind of tilted. And the spin of the black hole was not aligned with the axis of the astrophysical jets, and so as it sort of circled around, it was releasing materials in different fashion. And sometimes when the matter was no longer available, it would also do this, and this is kind of what we've observed. We've essentially observed this unusual pattern of bursts that we've never seen before, and right now the scientists are trying to explain why this is happening. But one of the main reasons is probably because the accretion disk itself is just not aligned with the spin, and because the black hole as it spins drags the space-time around itself, and because of that its astrophysical jet kind of wobbles a lot and produces these effects. Now, even though we've known about this black hole for a very long time, this officially is the first time we've detected something a little bit unusual about it. And although we don't really know that much about black holes just yet, we now know that they are a lot stranger and weirder than we initially thought. Now, one important thing to add here is that this accretion disk is actually really big. It's approximately 0.05 astronomical units, or about 5% the distance of Earth to the Sun. And because things here spin so fast and everything here happens really quickly, it will be very difficult for us to take a relatively accurate shot of what's happening here, except for something as simple as this. This is probably the best we'll do for quite a while. Unfortunately, because it's so far away, it's practically 8,000 light years away from us, and because everything here spins so fast, by doing a long exposure shot, you're only going to get a very blurry image. And by doing a short exposure shot, you're just not going to collect enough light to see anything. And because of that, it's somewhat difficult to explain what's really happening here. Now, we think that the accretion disk is misaligned with the spin of the black hole, and if so, we don't really know why, but one of the explanations is maybe because when this black hole was created, there was a large supernova that may have actually dislodged its spin. In other words, it created a bit of an angle in the spin of the black hole. But that's just one explanation. For all we know, something completely different is happening here, and we don't really know what. We do, however, know that the single orbit around this particular star, or technically the star's orbit around this black hole, takes approximately 6 days, and we also know that one of these outbursts is going to happen in the next 20 years or so, and we're going to be ready for it because we have new telescopes coming that are going to be able to see a little bit more. But until this next outburst happens, we're not going to unfortunately know much else about V404, even though it's been studied for several decades now. Anyway, so once we discover more about V404, I'm definitely going to come back and talk a little bit more about what we've learned, but for now that's it. So we know that this black hole spins with a very strange inclination and seems to wobble a little bit, and we seem to think that it's because of a possibly supernova that caused this. Other than that, that's really it. It's a strange black hole really far away. One day we'll discover something closer to us, but not yet. For now, this is the closest.
Hello wonderful person, this is Anton, and in this video we're going to be talking about yet another unusual, strange and mysterious black hole somewhere out there in our universe. But this time it's going to be a black hole that beats a lot of records. It is the brightest and also the hungriest or the most ravenous black hole we've discovered because it emits a tremendously bright light, brighter than the galaxy around it. I guess by now most of you have probably seen this image. This is M87, the ultramassive black hole, approximately 55 million light years away from us. And this one became a record holder because it was the only black hole that we were able to create a picture of from a tremendously large distance and also of a tremendously small point in the skies. But unfortunately, even though it's very massive, it's not really that bright. As a matter of fact, its brightness is actually quite large, but you can still see the shape of the galaxy around it, and you can also still distinguish a lot of other features. As well as, of course, the super long astrophysical jet that it emits that's approximately 4,000 to 5,000 light years long. In other words, even though it is pretty bright, it's far from being the brightest, and it's definitely not absorbing as much mass as it could. Now, when it comes to mass absorption for black holes, there's a term called Eddington limit. And that's the term that refers to the idea, the theoretical idea of a kind of a limit of any massive body to have luminosity or to have actual radiation pressure before it becomes too much and starts being more than gravity, at which point the object should just fall apart. For every black hole, Eddington limit is well known, and there are some black holes that seem to be really at the extremes of this limit. And today we're talking about one such black hole that's so massive and so bright that it seems to defy all logic and understanding of black holes. As a matter of fact, it might even be pushing its Eddington limit to the limit. Now, initially, this particular object was discovered in the mid of 2018 by a group of scientists whose paper you can find in the description below. And when they looked at it, it sort of resembled a typical quasar. In other words, a very, very bright object far, far away that seemed to emit a lot more light than it should. But the thing about quasars is that very often they're very difficult to distinguish from regular stars. As a matter of fact, when you look at their spectra, which they do provide in the paper, it sort of looks like a typical cool dwarf or a cool star. In other words, a star that's not too hot, not too warm. It also is not emitting any radio waves, so it doesn't really look like a galaxy with a black hole almost at all. Now there's a reason for that, and the reason is that it's really far away, and at this distance the light is really redshifted. It becomes more and more reddish, as you can see right here, compared to the galaxy that's a lot closer. In other words, because of the distances, what would be blue would appear maybe yellow or green or even in infrared light. And so because of the distances here, they were able to estimate that this galaxy is close to about 12.9 billion light years away from us, suggesting that it was already in existence approximately 800 million years after the creation of the universe. At the same time, this unusual galaxy named J2557-3602 was nothing like we've seen before. Its center was so bright that we could actually not even tell the rest of the galaxy apart. In other words, the black hole in the middle was emitting so much light that it was overshadowing the entire galaxy around it, completely making it invisible. And this is why we don't even know what the shape of it looks like. But then the scientists had to determine, is this really a quasar or could it still be some sort of an unusual star? And so they had to use the star movement data from the famous Gaia telescope by ESA to try to discover if there was any motion of this object. And they discovered that this object was not moving. It was basically just still in the night skies as if it was really, really far away, which it of course is, and at the same time being the brightest such quasar we've ever discovered. So let's compare it to something you might be able to imagine. In this case, we're going to use an object we're all familiar with, the moon. Now, if we were to go back to Earth and take a look at the brightness of the full moon in the middle of the night, it would be pretty bright. You can usually easily navigate around the beach, around the forest, around really anywhere, just using the night lights from the moon. And although it's not overwhelming, it is still pretty bright. Now, when it comes to this particular black hole, if we were to place it in the middle of our own galaxy at a distance of just over 27,000 light years away from our own planet, we would actually see something in the night skies that would be about 10 times brighter than the moon. And so let's try to imagine this by giving the moon some brightness. And this is sort of what you would see in the night skies, except that the actual size would be much smaller. It would only be a point, but a very, very bright point. And the other relatively dangerous thing about this point would be that it would be emitting a tremendous amount of X-rays and possibly even gamma rays pointing everywhere in the galaxy, including of course our own solar system. And all of this dangerous ionizing radiation would most likely prevent formation of any life on Earth. So in that sense, any galaxy that possesses such a black hole could actually struggle with creating anything worthy of life. Unless of course there is a type of life we don't yet understand, but the amount of radiation created in there is just absolutely mind-blowing. But at the same time, the scientists who discovered this particular quasar, which by the way stands for quasi-star, as I mentioned previously, sometimes they're confused for stars, and so it's sort of like a star, but not really. But to make sure that it's a quasar, and to make sure that the brightness was actually natural and not increased by anything, they had to also look for things like gravitational lensing that you see right here. So if there was another galaxy in front of this one, it could have actually given it a boost of luminosity, so maybe that's what we're observing. And to try to determine this, they used various bands of frequencies to try to see if there's another galaxy in front of it, and well, there was nothing. It was just a single spot. Which of course suggests that this particular galaxy is roughly around 20 billion masses of the Sun, around 3 times more than Poehi or M87, whose image we've taken in 2019, while at the same time being something like 700 million times brighter than our own Sun, while also being the fastest growing black hole we've discovered that seems to be absorbing matter ridiculously fast, eating up to about 1 mass of the Sun every 2 days. So in other words, in about a year or so, it consumes 180 to maybe 200 masses of the Sun. Now obviously, underneath all of this brightness and underneath all of this layer of energy, we'll discover just the same thing we always discover. A large, massive, and very powerful giant that's growing pretty fast. But remember, this is about 12.8 to 12.9 billion years ago. So this is what this black hole was like in the past. Today it might be completely different, but what's important here is that it creates a kind of a mystery. We don't really understand how these black holes can get so massive so quick after the creation of the first galaxies, while at the same time having such voracious appetites and being able to eat up so many masses of the Sun pretty much every single day. Now it's possible that it was a result of some sort of a collision between galaxies, or maybe several really big black holes came together and brought a lot of mass with them. But we don't really know. We just know that this is definitely the record holder for the brightest so far, and as I mentioned, it would be so bright if we were to place it in our own galaxy that it would overshadow our own moon. It would be one of the brighter stars in the night skies and also visible in the daylight, while at the same time being super dangerous, producing a lot of dangerous radiation.